Yeah, so I'm Adam Moreno, and I'm at the University of Natural Resources and Life Sciences in Vienna. And today I'm going to talk about spatial modeling with Biome-BGC. And I should clarify, really I'm talking about large-scale, spatially explicit modeling with Biome-BGC. And plus I decided to do something a little different and do a Prezi instead of a PowerPoint presentation. And Zoltan informed me that Prezi was actually developed in Hungary, so perfect. Let's see if the clicker works with it. It does. Okay, so Biome-BGC kind of started at this scale of modeling with a single tree. Steve Running at Oregon State just developed a simple tree model. And so this is where it all started, at this scale. Actually, maybe even at the leaf scale that we started at before, but most people don't model at this scale anymore. Now, maybe we're modeling at this scale where we have a forest with, similar or the same species in each forest, or maybe we do multiple types of forests within a larger area, like in Austria or Hungary. So in this case, maybe we have beech and spruce or something, but just a few species. And we can get some nice information from this scale about certain areas. But when we want to start asking big questions, like what should we do for climate change as a human population? You know, when the UN is talking, we need to start thinking about modeling on this scale. But, so I don't know anybody who's doing Biome-BGC simulations actually globally yet, for reasons I'll talk about. Maybe there are, but not me. But anyways, I'm going to talk about modeling on the continental scale, or at least, well, yeah, so Europe and the United States. So there's some advantages to modeling at this scale. There's some information we can get that we can't get at modeling at smaller scales. One is, for example, policy issues. Now, for example, RED is starting to move to this jurisdictional RED system, meaning that you can't just get carbon balances of your small area and do a RED project based on this. You have to know the carbon balance of a larger area. And so this is some work that I did at University of Montana. And this is simulated net primary production of rangelands. So this is unmanaged grass and shrublands. And so one of the advantages of actually simulating spatially all of the whole area is that if you just simulate just certain points in the different biomes, there's a lot of variation that you can miss in certain areas. High productive areas that are kind of in the middle of low productive areas and so on. And so as a policymaker, this gives you a good idea of, well, exactly what's happening spatially over your whole area. So you can create, very specific policies for different areas. Also, all of the data is continuous and harmonized at this scale. So you don't have to worry about having simulations that were done by different people in certain areas and trying to make them harmonized so you can get analysis of the whole area. This way, all of the data is on the same scale. It's done using the same methods, and it's easier to analyze this way. Yeah, and so here is a map showing, this was a projected simulation. So doing future projections of net primary production. And this is showing the slope of the linear regression of each point. So whether the NPP is increasing or decreasing in certain areas. And so if you just modeled certain points, yeah, you can't really interpolate this sort of data. You actually have to go and simulate every point because every point has its own special characteristics that will either make it increase or decrease. And also it gives you a totally harmonized and holistic view of your data. So yeah, it's not just mountains, but you're seeing what's happening in the mountains and what's happening in the prairies and in the desert lands. And so also with this, you get to try some new methods that are kind of interesting. So this is kind of maybe a new validation exercise that I tried. So this is just showing the primary drivers of net primary production during this 100-year period. So this red is driven by temperature, and this is driven by precipitation, and this actually by solar radiation for some strange reasons that I found out. But the point is that these areas kind of followed the biomes that we would expect. So it was kind of a nice validation of the model to show that, well, if you're not just looking at flux tower data, maybe each point at the flux towers is not accurate, but over the whole entire spatial area, the model is working it's working in a realistic way because it's following certain biome types. Okay, so modeling at this scale, we can address some policy relevant issues. The data is harmonized, continuous coverage, and you get a holistic view of your whole entire area. So if there's so much good information we can get from this modeling, why doesn't everybody do this large-scale spatial modeling? Why is it so hard? Well, there's a few reasons, I think. First, data. There's input data set issues. So Biome-BGC requires tremendous amounts of input data. Soil, climate, nitrogen deposition, your cover types, a DEM. So you need to make sure that there's actually data to cover your whole entire area. So maybe at the globe, this would be a nice simulation to do, but can you find all of these input data sets to do the entire globe? That's the problem. But also data accessibility. So this is one interesting challenge I found coming over to Europe and trying to do this type of modeling. Well, I should say right now I'm trying to do a 1 by 1 kilometer resolution simulation of all European forests. So I'm having to come up with all of this data along with a lot of our partners in this EU project who several people here are a part of. But part of the problem is data accessibility. So maybe these data sets exist, but can you get to them? This is kind of a problem that Europe has that I didn't experience in the United States. For example, weather station data. If I want to do my own daymet simulation in the United States, well, this is pretty easy. I can get weather station data, at a click of a button pretty much. But in Europe, there's no harmonized weather station network. I mean, there are freely available and public weather stations, but not all of them are included in this. And so this accessibility issue is difficult. Scale of the data, of course, always difficult. Back to climate issues. So if you want coverage of all of Europe, it seems that the choice to go with is EOBS. And EOBS is at the 1 day time step, which we need for Biome-BGC, but it's at 30 by 30 kilometers. So if you want to go any lower than 30 by 30 kilometer resolution, you need to do some sort of downscaling. So anyways, just an example of scale issues. Yeah, and data coverage. So I've ran into this problem with the soil data, for example. So I can get maps of Europe very nice soil maps of Europe done by the Joint Research Institute, JRC Center, yeah. But, you know, Switzerland and Norway are missing. So how do you fill in these gaps? You know, you need to find different data sets that cover these areas. Just another challenge. Okay, so yes, data problems or challenges. Also, parameterization and validation. Cover types. So when you're doing, say, a run of just Austria, it's enough to have EPC files of beech and Norway spruce. And you can get a pretty accurate representation of Austria. But when you're trying to do all of Europe, well, you can't do an EPC file for every species in Europe. For example, the EFI cover type map has 20 different species estimated. So to create an accurate parameterization file for each species would be a nightmare. I mean, it'd be a nice project if somebody wants to do it. So I guess this is the place to address that. So maybe you need to come up with clever groupings, different forest types, and things like that that generalize species groupings. And so you need to think about that. So after you have your different cover type groupings specified, well, how do you even begin to parameterize them? You can't just go into the literature and find your special group and get the parameters you need. You can't go into the White 2000 paper and just take those parameters and expect them to work. You have to, well, it just doesn't exist in the literature. So you basically, I don't know, find something similar, start from there, and then you move forward and parameterize yourself. But then, of course, you're covering huge areas. So you have these latitudinal gradients, and you know, this is always something people have questioned with these methods that I've been using. You know, you can't have, if you parameterize a Norway spruce in Austria, is it going to grow the same in Norway? You know, so when you parameterize for large spatial areas, you need to somehow have a clever parameterization scheme that will generalize a species type or a forest type over these large areas. Anyways, also a challenge. And validation data sets. So traditionally, maybe some people go to flux tower sites and validate their models via flux towers. But when you're thinking of huge areas at high resolution, even if you use all of the flux tower sites in Europe, this is not statistically significant to the amount of points that you have. So you have to come up with other clever ways of validating your data. Like, for example, with the biome type thing that I showed. Or you validate against MODIS. But you know, MODIS is also a model. So it's a model validating against a model, and some people don't like that. Or you can validate against NFI data. But this is also a problem of getting all of the NFI data, harmonizing it, and getting it into a way where you can actually validate your model against it. Yeah, and then, you know, there's the nuts and bolts, the software and hardware issues that come along with this. So this is massive, massive data sets. So for the run that I'm doing, it has approximately 9.5 million points. And it's terabytes and terabytes of information. So you have to have a place to store this, and you have to know how to process it and have clever ways of analyzing this huge amount of data. Like right now, at Boku, you know, we just bought you know, a new server so we could process this data, and we're trying to get more storage. It's just huge amounts of data. Yeah, and as Alex pointed out earlier, yeah, scientists with programming background, this is also a challenge. Because well, yes, you need to know how to program to be able to work with Biome-BGC and create the scripts and analyze and all of this. But not only do you have to know how to program using these massive data sets, you need to be able to program at a slightly higher level, being able to multi-thread and multi-process all of your data. And you know, some people, maybe a professor who hasn't done this type of programming before will tell their student, oh, you know, let's take Biome-BGC and put it on this supercomputer and let's run this huge simulation. But I'm sure, you know, anyone who's done any supercomputing knows you can't just take a model and throw it on a supercomputer and expect it to take advantage of the architecture. You have to reprogram it so that, you know, whether it's using MPI or some other parallel processing system, yeah, it just takes a higher level of programming to be able to deal with these in a time-efficient way. Well, yeah, and me and Christopher the other day calculated how long my Biome-BGC simulations would take without multi-threading, without multi-processing. And it was something like 1,000 days or something like that. So that's completely unrealistic. But you know, with the multi-processing, it should take about a month, which is still a long time, but not a few years anyways. Yeah, and then all of this takes money at this level because it's expensive to buy all of this storage or a new server or the programs you need to be able to visualize and analyze the data, whether it's Imagine or Envy or whatever. But then also you need the expertise to be able to utilize your hardware and utilize your software. Yeah, and then all of this takes time. Every data set that goes into these simulations, as you all know, is one small project in and of itself. So every step of the way takes time and has its own problems. Not to even address just the processing time it takes with huge amounts of data. So anyways, that's my presentation. Thank you.